In the last section, we spent a lot of our time talking about how to find the derivative of a function, and we used that long limit definition. We said, okay, limit as h approaches 0, f of x plus h minus f of x, all of that divided by h, and that was what told you your derivative. And you can always fall back on that, but it's a very long process. It's a very tedious process. So in this section, we're going to see if we can talk about ways, or if we can find ways to speed this process up, just to make the process of finding the derivatives a little bit easier, so that we can do other cool stuff with the derivatives. So first thing that I would like to do is talk about some notation. If you have a function y equals f of x, f prime of x, y prime, and dy dx all represent the derivative of f. So these are all talking about the derivative of f of x. Most of the time we'll be using f prime of x and y prime. That just tends to be what students are most comfortable with. But if you see dy dx, or there might be a time or two where I think that this notation is beneficial to use, know that we're talking about the same thing. It's just another way to talk about the derivative. So let's get into our first shortcut here. And in order to do that, I want to remember that the derivative of a function always tells us the slope of the tangent line. And if you were to sketch a constant function here, so f of x equals c, the slope is always 0. So let's draw out a constant function here. I'm going to draw the function, how about y equals 3 right here? So 1, 2, 3. A constant function is a horizontal line at that particular y value. I'm going to make that line just a little bit thicker right here, just so that I can sketch the tangent line on there and still see this function. So here's the function y equals 3 if you were to graph it. And let's suppose that I wanted to sketch in the tangent line right here at x equals 1. I just picked an x value at random here. So at x equals 1, what would my tangent line look like? Well, it would sort of just sit on top of that function itself, and then I would ask the question, okay, well, what's the slope of that red line? Well, the slope of that red line is 0. So, okay, the slope at x equals 1, we just said the slope was 0. Okay, so let's maybe try a different x value. Maybe we'll get something different. Over here at -2, if I picked that, and I sketched in the tangent line, well, again, it would just kind of be a function sitting right on top of that, on top of y equals 3. And again, I would ask myself, well, what's the slope of that red line? Well, that red line, it's just right on top of the blue line, which has a slope of 0. So again, we have a slope of 0. Let's say I wanted to try something really different. I picked, x equals 1,000 way over here. And I sketched in the tangent line. Well, the tangent line again would look something like this, be another horizontal line. And again, I'm going to ask myself, well, what's the slope of that tangent line? Well, once again, hopefully, unsurprisingly, it's 0. It doesn't matter where we draw the tangent line. You're going to have actually the same exact tangent line, and the slope of that tangent line is always 0. So this gives us our first shortcut right here. Let's draw this off to the side. It says if you're working with a constant function, if f of x is equal to c, right? C is just some number. Then the derivative of that function, then f prime of x, is just equal to 0. So if you start with a constant function, the derivative of that constant is 0. There's no work to be shown. That's really all there is to it. You can use that as a fact going forward. So if I want to find the derivative of the following functions here, so first I have f of x equals -24. Well, if I took the derivative of this, maybe I said, all right, f prime of x, -24, that's a constant. It doesn't depend on x, so the derivative of that must be 0. Well, that's cool. Y equals 12. If I were to take the derivative there, if I said, all right, let's use dy dx here. Again, remember, this is just another way to talk about the derivative, but the derivative of 12, where 12 is just a constant, well, we just said the derivative of any constant is 0. So there we go. y equals 0. This one might be a little bit tricky, but remember that 0 it's a special constant, but it's still a constant. It doesn't depend on x in any way. So the derivative of a constant, we said, was 0, so the derivative of 0 must be 0. Lastly, f of x equals pi. Be careful with this one. Remember that pi is a number, right? It's a constant, 3.1415, blah, 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 blah. It's got that really long decimal, that infinitely long decimal. F of x equals pi is a constant. It's an irrational constant. It's an ugly constant to work with, but it's still a constant. So the derivative of that constant must be 0. So that is our first derivative property. Really, really nice, but it is kind of a narrow scope. It doesn't cover a whole lot of ground. It tells us how to take the derivative of constants, but not a whole lot more. So now I'd like to just turn my attention to polynomials, some simple polynomials here. And if this were a face-to-face class, I'd have you guys work out a few of these derivatives. So I would say find the derivative of f of x equals x. And I'll just tell you guys right here that the derivative here, f prime of x, is equal to 1. And then I say, okay, well, let's try and make it a little bit more complicated. Let's try x squared. So we'd go and take the derivative of x squared. I'll tell you f prime of x in this case is 2x. Then I say, okay, well, let's try it again, x to the third power. It'd be kind of a pain, but you could do it. The derivative of x cubed, f prime of x, would be 3x squared. And then, okay, at this point, some of these derivatives get really hairy and really ugly. So I would just start to say, I'd tell you, it's okay here, for x to the fourth, f prime of x, that is equal to 4x cubed. Find the derivative of x to the fifth. I tell you, okay, well, the derivative of x to the fifth, that derivative is 5x to the fourth power. And then I'd look back and say, okay, well, look at all of these derivatives. If I start with x, the derivative of x is 1. X squared, the derivative is 2x. X cubed, the derivative is 3x squared. X to the fourth, the derivative is 4x cubed. X to the fifth, the derivative is 5x to the fourth. So hopefully we're kind of looking at these and we're identifying a pattern. In particular, I want to identify what's going on with my power of x and then how that impacts both the coefficient of my result and then the resulting power. Here I didn't write a power, but 2x is really the same as 2x to the first power. So what we're going to do every time here is we're going to use this thing called the power rule, which is really, really helpful. The power rule says if you have a function x to the nth power, then the derivative is n times x to the n minus 1. So if you're using the power rule, you essentially have two very small steps to do when you're taking a derivative. You are going to start by taking this power, you are going to multiply by that power. So I'm going to multiply by that power. So notice here is n, and then I multiply here by n. So we multiply by the power of x, whatever it is. And then, okay, what happens to that power? Well, if I start with n, I end up with n minus 1. So my second step would be to subtract 1 from that power. And this is huge. This gives us a really, really nice way to evaluate derivatives. It speeds up the process tremendously. So if I wanted to continue, we're going to look at just a bunch of different examples here because having a solid understanding of the power rule is going to be really, really, really important. So I'm going to come back to these exponent rules when I need them, so we'll revisit these. But for now, if I wanted to start with here, f of x equals x to the sixth, I want to find f prime of x, so f prime of x. So we're going to multiply by our power. We're going to multiply by 6x, and then I'm going to subtract 1 from my power, 6x to the fifth power. So hey, there we go. y prime equals y prime for y equals x to the 30th power, here I'm going to say, okay, y prime, I'm going to multiply by my power, which is 30 times x, and then I will subtract 1 for my power, so 30x to the 29th power. Hey, there we go. Next up, we've got a slightly different notation here, dy dt, but this just says find the derivative of y with respect to t. So this is still just a derivative, and notice here my variable's changed, and that's okay. It's not going to make a big deal. Sometimes we'll use t rather than x. But I want to find dy dt for y equals t to the negative 2, and you might look at that negative 2 and say, oh my goodness, how is this going to change my process? Can I use the power rule here? Don't worry. The negative exponents do not impact our problem in any really meaningful way. We just have to be a little bit careful here. So when I go and take the derivative, dy dt, I'm going to start by multiplying by that power. So I'm going to multiply by negative 2t. And then I'm going to subtract 1 for my power. And here you want to just be really careful. I want to take negative 2 minus 1. Or really negative 2 plus negative 1, which is actually negative 3. So my new power, oops, I don't know why that changed that there. My new power should be negative 3. So I should end up with negative 2t raised to the negative third power. So just be very, very careful with your minus signs and your negative signs here. It's really easy to make a mistake and kind of forget if you subtract 1, that number is actually going to look a little bit bigger if it starts off negative. So then, okay, well, let's look at d. Oh my goodness. This is a new notation here. So this I want to talk about here. d dx right here, this is also a notation for the derivative, but this is, when we talk about like y prime or f prime or dy dx, I sort of think of these three things as nouns. It's really saying, it's talking about the derivative. The derivative is a thing, it's an object. So it says, okay, this is what the derivative is. It's, 30x to the 29th, or negative 2t to the negative third power. This guy instead over here, this d over dx, this is a verb. When I see this, what I think, this guy right here, this d dx, really says take the derivative of whatever follows afterwards. So take the derivative of this guy, and that's going to be of x to the 3/2. So it's really telling us to do the same thing that we've been doing. It says take the derivative of that power. Of that function. So we just take the derivative and go, okay, this one's maybe, again, a little bit worrying because we have fractions. How is that going to change our problem? Well, luckily, not very much at all. So I'm going to take the derivative, I'm going to multiply by my power. So rather than saying y prime equals or f prime equals, I don't necessarily know that those are y prime or f prime. So I'm just going to say the derivative is equal to. So I'm going to start by multiplying by my power, multiply by 3/2 x, and then I'll subtract 1 for my power. So here we might just need to do a little bit of mental math here. I really have 3 over 2 minus, this is 1 over 1. But I know that 1 over 1, that's really the same as 2 over 2 would give me 1/2. So my new power is 1/2. Here's my derivative. So fractions don't really change our problem that dramatically. Part E, here I have f prime of x, for f of x equals x to the 1/2. So again, we're just taking the derivative of this. Here we have a fraction, but we know from the last example that it's really not going to change our process all that much. F prime of x, I'm going to start by multiplying by my power, 1/2 x. And here we might need to be a little bit careful, because if I subtract 1/2 minus, 1 is the same as 2 over 2, I actually end up with a negative number, 1/2. Don't overthink these problems. That just means that my new power is negative 1/2. So I have 1/2 x to the negative 1/2. You could leave your answer like this. However, I think when we're working with negative exponents, I think that negative exponents are more difficult to work with algebraically, simply because we don't have as much experience working with them. So I would encourage you to rewrite that with a positive exponent, particularly because later on in the course we're going to be doing more with these derivatives. Even in this section later today, we're not just going to focus on finding derivatives, we are going to be using them. So I always like to rewrite them with a positive exponent, and the way we do that here, we go back to our exponent rules, is this guy right here. If you have a negative exponent, you can turn that positive, or you can make that positive by bumping that power of x down to your denominator, and then you make the power of x positive. So this is going to be a really, really important rule. Even if you don't rewrite these types of problems, some of these we are going to have to rewrite. There's just no way around it. But for this one, it's kind of optional. If you were to type this into my math lab or give that to me on an exam, that's fine. But I'm going to rewrite this with a positive exponent. I'm going to rewrite this as 1/2. This is really 1/2. When I convert this guy right here, this will be 1 over x to the positive 1/2. Or it would probably be easiest to write this as 1 over 2x to the 1/2 power. So you could write like this, or no, we'll hold off on that. This, I would say this or this is what I'd be looking for. Either one perfectly fine. Let's keep going here. F, I have dy dx for y equals x. And I sort of hinted at this one offhanded earlier. We said, okay, if we go back earlier, we said, hey, the derivative of f of x equals x, that's actually equal to 1. Well, why is that? That one seems maybe a little bit different from our other polynomials here. So let's think about this here. If I start with y equals x, this is really x to the first power. If we don't write that power, we assume that x is to the power of 1. So if I wanted to take this derivative dy dx, I would multiply by my power 1 times x, and then what else do? We subtract 1 from the power. So 1 minus 1, that would give me 0. But anything to the 0 power, I know, is 1. So I really have 1 times 1, which is just 1. So that's why that one is the way it is. That's why the derivative of x to the first power is simply just 1. It looks a little bit different, but it's still following exactly the same rules as all of the other problems that we've looked at. Here in part G, this one's a little bit tricky here. G, I have h of x equals 1 over x. Notice for our power rule, if we go back and look at our power rule, this says x to the nth, so that x has to be in the numerator. I can't take the derivative of a power of x while it sits in the denominator. So here is where these exponent rules are going to start to come into play, and here's where I have to use this one. There's really no way around it right now. I need to take that power of x and rewrite it with a negative exponent so that I can bump that up to the numerator. So right now, this is really 1 over x, we said, to the first power. Oops, let me rewrite that. This is really 1 over x raised to the first power. But I can't take the derivative with this x in the denominator, so I'm going to bump that x up to the numerator to say x to the minus 1 power. Now, this is something that I can take the derivative of. Now for that, I say, okay, well, h prime of x, I'm going to multiply by my power, negative 1, x, and then I'll subtract 1 from my power. Negative 1 minus 1, again, be careful with your negatives here, should be to the negative 2 power. So you could leave your answer like this, and that'd be perfectly fine. But if you want to write it with a positive exponent, I would write this as negative 1 all over x squared. Either one of these is perfectly fine. So these exponent rules are going to be something that we need to memorize here. H, I have y prime. I want to find y prime for y equals the cubed root of u squared. This one's difficult because it doesn't even look like x to some power here. Here I have u, but honestly, that's not the big problem. The big problem is the root. It's the radical. How do I deal with that? Well, luckily for us, we have these exponent rules up here, and here's where we're going to use that second one. This says if you have the bth root of x to the a power, I can rewrite that as x to the a over b power. So that means that I can take this function and I can rewrite this as u raised to the 2/3 power. Now this looks more like something that we've dealt with. Now this actually looks similar to parts D and E here. So I can take the derivative. Y prime, I'm going to multiply by my power, so 2/3 times u, subtract 1 from the power. So here I have 2/3 minus 3 over 3, that's really negative 1 over 3. Could leave your answer like that, or if you wanted to, we could rewrite it with a positive exponent and say 2 over 3 u raised to the 1/3 power. Either one of those would be fine. I would take either one of those as your answer. Kind of similarly here we've got all sorts of problems. Here this says, again, take the derivative of 1 over square root of x. Well, this is all sorts of complicated. So, okay, I want to take the derivative of 1 over square root of x. We're actually going to have to use both of our exponent rules here to rewrite this. So this says take the derivative square root of x. And this might just be a good one to know. If you're working with specifically square root of x, first of all, we said if you don't have a power of x, we're going to assume it's 1. And I believe we talked about this earlier. If you don't have an index of your roots, it's a square root, we're going to assume that it's 2. So square root of x is really x to the 1/2 power. So I have d dx 1 over x to the 1/2 power, which is better, but I still have this power of x in the denominator. I can't take the derivative of a power of x that's in the denominator. So I need to bump that up to the numerator. So I need to say that this is really x to the negative 1/2 power. Now I'm good to go. Now I'm ready to take the derivative of this. So I will multiply by my power, so negative 1/2 x, subtract 1 for my power. I'm really subtracting 2 over 2, so my new power should be negative 3 over 2. You could leave your answer like this again if you wanted to just leave a negative exponent, or if you wanted to practice rewriting it with positive exponents, negative 1 all over 2x to the positive 3/2 power. Either one of these is perfectly fine. Now, one thing I want to talk specifically about the last 3 problems. Notice in each one of these, in G, in H, and in I had to do a little bit of rewriting here. I had to rewrite 1 over x to the first as x to the negative 1. I had to rewrite the cubed root of u squared. I had to rewrite that as u to the 2/3 power. 1 over square root of x, I'd eventually write that as x to the negative 1/2 power. Notice that for all of these, I didn't stop right there. I didn't actually take the derivative. This is not h prime, right? I didn't do the power rule. The power rule says I need to multiply by my power and subtract 1 from my power. That's not the derivative. I just rewrote it so that I could take the derivative. Same thing right here. U to the 2/3, that's not y prime. Oops, not y prime, because I didn't multiply by the power and subtract 1 from the power. Same thing right here. This is not the derivative because I haven't applied my power rule. I haven't multiplied by my power and subtracted 1 from my power. The reason I'm kind of making special note of that here is because this is a really common mistake I see students make all the time. I'll see students rewrite their function. They'll rewrite the function and then they'll say, you know what, this guy right here, that's my derivative. But you're forgetting the most important step. You're forgetting the part where we multiply by the power, subtract 1 from the power. You're forgetting the power rule. So please make sure that in these problems that we rewrite it, we don't forget to also apply our power rule. We have to do both of those things. Last one, J right here. J, I have the derivative of 5x cubed. And this one I'm sort of just you know what? I'm going to leave it as a cliffhanger here. I'm going to say, okay, what do you think that this should look like here? Really, the only difference here now is I have this coefficient of a 5. Is that going to change our problem dramatically? Is that going to change our power rule all that much? Do we have to learn a whole new rule just to deal with these coefficients? Or would it behave the way you would expect it to? Most students look at that and say, boy, it'd be really nice if we multiplied by the power. So we multiply by 3, 15x, and then I subtract 1 from my power, 15x squared. Is that the case? Well, you're just going to have to tune into the next video to find out. So I'm going to leave and end this video right here, and you're just going to have to go jump right into the next video to find out the exciting conclusion of this question.